for hosting me. So let me start the screen share. This and then play the presentation. Oops, gotta do this thing. All right, and just again double checking that you're seeing the main slide.
Yep.
All right, cool. All right. So this poll that we had before the presentation is actually a perfect segue into the presentation, because I think it's always important when starting to talk to make sure that you're defining your terms. So let's define what light is. For those of us with sight, light is one of the main ways that we learn about the world around us. But if you were to ask a physicist, they will tell you that light is both a particle and a wave. And it's the wave aspect of light that we're going to talk about, because the wavelength of light, the distance from one peak to the next peak, encodes a lot of information about light and determines what we're ultimately able to observe. The shorter the wavelength, the more energy that the light carries. And I picked these colors on purpose because blue light has a shorter wavelength than red light. And we can see that white light is made up of a bunch of different colors. And we have some experience with this. If we see white light being refracted, whether it's by water droplets in our atmosphere, that causes a beautiful rainbow, or if it's light being dispersed through a prism. And the colors that we see in dispersed light always follow the same order. And if you're like me and in elementary school, you learned the acronym ROY-G-BIV, red, orange, yellow, green, blue, indigo, violet. Those colors are always in the same order because it depends on the wavelength of light. And visible light, even though it's the winner of the poll and it's everyone's favorite light, it's just a sliver of the overall electromagnetic spectrum. We have light that is more energetic and has shorter wavelengths, including the ultraviolet, X-ray, and gamma ray, which got no votes, no love in that poll, as well as light at longer wavelengths, infrared, microwave, and radio. So we can't see most of this light with our eyes, but the universe doesn't care. Everything from planets to stars to galaxies to the very seeds that created the universe that we see around us today give off light across the electromagnetic spectrum. So if we want to truly understand the universe and our place in it, we need to build telescopes to observe light that would otherwise be invisible to us. And as astronomers, we've done this for decades. We've built telescopes that could observe light across the electromagnetic spectrum. And NASA's great flagship observatories have also built telescopes to observe light across the spectrum. So most people are probably familiar with Hubble. It was launched in 1990, and it observes visible light and a little bit of infrared and some ultraviolet. And it's kind of just hard to understate the impacts that Hubble has made to our understanding of the universe, as well as fundamental physics. And the images and discoveries from Hubble rightfully fill us with a sense of awe and wonder about the world around us. Hubble is just one of the 4 great observatories. So these are NASA flagship missions, which means that they're ambitious missions, telescopes that are launched into space to give us the most detailed view of the cosmos yet. So other flagship missions are the Compton Telescope, which observed gamma rays, the Chandra Observatory, which observes X-rays. And it has a special place in my heart because before I started grad school, I used to work for the Chandra Observatory as a mission planner for a few years. So I'm a little bit bummed X-rays only got 1 vote in the poll prior to this talk, but you know, it's okay. X-rays are a great view of the universe, and maybe if I come back another time and tell you all about it, maybe I could convince you that X-rays could be one of your favorite wavelengths too. And the Spectr Space Telescope observed in the infrared. And of these 4, only Hubble and Chandra are still operational today. The next generation of space telescopes follow in this tradition, JWST being the first one of those. And that's slated to launch later this year. The next flagship mission is the Nancy Grace Roman Telescope, which is scheduled to launch mid-2020s. And just today, so I've given a version of this talk twice, and this last panel to the right was a big question mark because I did not know none of us, well, several people on the planet knew the answer to this. But just today, the decadal survey results were announced, which is the process by which scientists and astronomers from around the world write papers to talk about where they think the major discoveries in the future will come from and the type of telescopes that we need to support that. And it's input that goes into the National Academies of Science that writes a report to prioritize where funding should go to make this vision a reality. And we've been waiting a while for this report to come out, and it came out this afternoon. And what was prioritized for space missions for NASA in the future is a large infrared, optical, and ultraviolet telescope. So that's similar to Hubble in terms of the light that it observes, but will be 3 times larger than Hubble and much more sensitive. They also recommended some development on X-ray probe and far infrared probe missions. So these would be not as expensive, but still would push the envelope further than what we know today. And by kind of investing in these multiple programs, it gives us that ability to recover a little bit of what we had in the era of great observatories, where we had these missions in space that observed across the electromagnetic spectrum. And if you really want to understand the universe, that multi-wavelength coverage is very important. So JWST is the next big flagship mission for NASA that's being developed in partnership with the European Space Agency and the Canadian Space Agency. And it observes infrared light. If you're curious about numbers, the wavelength of light that JWST observes spans from about 0.6 microns to 28 microns. So that region is shown by the gold rectangle. And the discovery of infrared light is an interesting story. And like many great discoveries, it begins with an observation, noticing, this seems interesting. Let's look at this a little bit more. Around the turn of the 19th century, William Herschel realized that colored filters seem to have different temperatures. And he set up an experiment to test this, where he took a prism and dispersed white light to its constituent colors, and then took thermometers to measure the temperatures of those colors. He found that red light was hotter than green light, and green light is hotter than violet light. He then repeated this experiment, but this time with a twist. He added a thermometer beyond where he saw red light, and he measured the highest temperature. And he looked into this. He started switching out the thermometers just to make sure there wasn't a problem with the equipment. But no matter which thermometer he put there, he always got the same result. What he was seeing beyond the red light had the highest temperature. He published a paper in 1800 that said, it's evident that there's refraction of rays coming from the sun, though not fit for vision, are invested with the power of occasioning heat. He termed this light calorific rays, and it's what we now refer to as infra or beyond red. Observing in the infrared gives us a unique view of the universe, a perspective that we can't have at other wavelengths. One of the ways it gives us a unique view is something that William Herschel touched upon a little bit in his observations. Basically, anything that gives off heat gives off light. And where on the electromagnetic spectrum that light is given off depends on the temperature of that object. So hot objects give off more light at shorter wavelengths, while cooler objects give off more light at longer wavelengths. So the sun is about 5,500 Kelvin. And so its peak wavelength is right in the visible spectrum, right in the middle, about half a micron. So it's not surprising, perhaps, that our eyes have evolved to be able to be sensitive to visible light. The human body is certainly not as hot as the center or the atmosphere of the sun, which is a good thing. Our temperatures are about 305 Kelvin, which corresponds to a wavelength of about 9.5 microns, or well in the infrared. And this is how night vision goggles or cameras work, is that these are detectors that are tuned to pick up light that has wavelengths where our temperature peaks, or the temperature of animals peak. If we want to extrapolate this to outer space, there's just some objects that are relatively cool, that are not nearly as hot as our sun or some other very hot stars. Stars that are much cooler give off much more light at infrared wavelengths than they do at visible wavelengths. So if we want to study those stars, we have to have infrared capabilities. Asteroids in our own solar system, sometimes we could see them by the sunlight reflecting off of them. But from their own temperature, we could observe them using the infrared. And this class of objects called brown dwarfs, which are not quite planets, not quite stars. They're not large enough to be to fuse hydrogen into helium into their cores, so they're sometimes called failed stars, but they're much bigger than regular planets. Those are also really good emitters of infrared light. Another benefit of observing in the infrared is that it helps us to peer through the dusty veils in the universe. This is a visible image of the Carina Nebula, and a nebula is a cloud of dust and gas. And it's a striking, beautiful image where you're seeing this cloud being illuminated by stars around this cloud and behind the cloud. The wavelength of visible light is about the same size as the dust particles. So the light from the stars behind this nebula gets scattered by that dust. Infrared light has longer wavelengths, so it's able to pass through that dust cloud. And so by observing in the infrared, we could see all the stars that are behind this nebula, including the star in the upper left that has these jets shooting out to either side of it. So as you can see, having both the visible light image and the infrared image give us a much fuller picture of the universe than if we didn't have that capability. Observing in the infrared also gives us the ability to see the distant universe, because we could use the Doppler effect to our advantage. So an example of the Doppler effect is if you're standing on the sidewalk and an ambulance drives by you and its siren is going, as an ambulance moves away from you, the pitch of the siren sounds lower and lower and lower and lower. And that's because the sound wave that's coming from that siren, as the ambulance is moving away from you, the wavelength of that sound wave is increasing to longer and longer values. And we hear that being manifested by a lower and lower pitch. We know that the universe is expanding. And as it expands, it takes galaxies along for the ride. So as light is coming from these galaxies that are moving away from us, light that originally starts out at optical or visible wavelengths or ultraviolet wavelengths, young massive stars give off lots of ultraviolet light. As that travels through the universe that's expanding, the wavelength of that light gets stretched so that by the time it reaches our telescopes here on Earth, what we observe is infrared. So this gives us the ability to see the distant universe. JWST will observe the infrared universe using 4 different detectors, has 4 science instruments. So it's like getting 4 telescopes for the price of 1. 3 of them observe at near-infrared wavelengths, and 1 observes at mid-infrared wavelengths, so at longer wavelengths. If you want the numbers, the wavelength for the near-infrared instruments, that's sensitive to light that has wavelengths between 0.6 to 5 microns, while the mid-infrared detector is sensitive to light between 5 to 28 microns for that wavelength. I want to highlight this little guy here, the near-infrared imager and slitless spectrograph, or NIRISS, because this is the instrument that I work for. I am the manager of the team that's responsible for the science operations of NIRISS. And NIRISS is a contribution from the Canadian Space Agency to the JWST mission. So in addition to having these 4 science instruments to observe the infrared universe, JWST has a very large mirror. It's in fact the largest telescope ever to be sent to space. The diameter of this mirror is about 6.5 meters, and it's made up of 18 segments. And here are some additional pictures of the JWST mirror, which doesn't really add any new information to the talk. I just put them in because they were pictures that I took back when I was a postdoc working at the NASA Goddard Space Flight Center. At that point, the instruments and the mirrors were being assembled at NASA and being tested. And there's a little viewing room that you could go to take pictures of the mirror. So this was from 5 years ago. All right, so there is a challenge if you want to observe the infrared universe and you want to do it in a way that's as sensitive as possible. Anything that gives off heat, gives off light, and if it's something that's cooler, it's going to give off infrared light. So if you want to make JWST as sensitive as possible to infrared light from the cosmos, you have to keep JWST cold. One way to keep it cold is to put its orbit as far away from the sun and the Earth as possible. So where JWST orbits is this position called the Lagrange point 2. And it's where the gravity from the sun and the Earth balance the orbital motion of a satellite. So this is past the sun, obviously, past the Earth, past the moon, and it's about a little bit under 1 million miles away from the Earth. So this helps. Gain it as far away from objects that give off heat helps, but it has to be kept colder still. And one way that it's kept colder is shown a little bit in this image, where what's facing us is the telescope, and underneath is this kite-shaped shape. And what that is a sun shield. This thing is enormous. It's the size of a tennis court, and it's made of this strong, ultra-thin material, which is really a success of material science and engineering. And it has this kite shape to deflect heat off of the sides to keep the telescope and the science instruments cool. So it has 5 layers, and each layer allows less and less and less heat to transmit through. That if you compare the hot side to the cold side, there's a 573 degree Fahrenheit temperature difference. So this works well for the near-infrared instruments to keep it what we call passively cool. And it means that those instruments will operate at a temperature of about 39 Kelvin, maybe a degree or 2 lower. And for reference, 0 Kelvin is absolute 0. Can't get any colder than that. For the mid-infrared instrument, that has to be kept even colder, because mid-infrared is observing longer wavelengths, so it's going to be more sensitive to any heat. So there's a cryocooler that's turned on so that the MIRI instrument can operate at a temperature of about 7 Kelvin. Okay, so JWST is going to be great because it's going to be very sensitive to infrared light. It has a huge telescope. So you have this huge light bucket to collect as much light from the universe as possible. But herein lies the challenge. How do you fit a telescope that has a mirror that's 2 stories tall, a sun shield that's the size of a tennis court, within a fairing that's only 16 feet? And the answer shows ingenuity. You fold it up like origami and you could get it to fit. That leads to another challenge because then it needs to unfurl in space. So these are just some of the reasons why JWST is so innovative and challenging. But if you want to really make great revelations in our study of the cosmos, you have to embark on challenging missions. And Thomas Zurbuchen, who is the Associate Administrator of the NASA Science Mission Directorate, noted in an email to the project in August that Webb is the Apollo program of NASA science. This is the level of complexity that we've been undertaking over the past number of years. It's the largest telescope to be launched into space. And again, you got 4 science instruments, so it's like 4 telescopes for the price of 1. In order for it to be sensitive to infrared light from the universe, it has to stay cold, which means the orbit has to be about 1 million miles away. You need to block additional light from the sun using these sun shields. And you may have noticed it has an open design. Unlike every other telescope launched into space that's enclosed in a tube, or telescopes on Earth that have domes, JWST is open. And this is, again, to minimize background in the infrared, because if it was enclosed in a tube, it would have heat from that enclosure, which would give off infrared light. And I actually have a lithograph from 1998 that showed different design concepts for JWST while this mission was first being developed. You can see which one is closest to what we have today. And then because it's so large and we don't have a vehicle that's large, and a launch vehicle that's large enough to hold it, it has to be folded. And that's a challenge. And then all the deployments after launch, about 50 of them, it's also a challenge. If we want to do a more direct comparison of JWST with Hubble, probably everyone's most well-known space telescope, there's differences in the type of light that they do observe. Hubble, again, we all know it observes optical light. We've seen these stunning pictures. It also observes an ultraviolet and a little bit of the infrared. So there is this region in infrared light where JWST and Hubble overlap. But in that overlap region, JWST is much more sensitive because, again, it has a much larger mirror. So if we compare the mirrors between Hubble and JWST, you can visualize what that size difference is. So the Hubble mirror is maybe about 8 feet. It's 2.5 meters, a couple feet taller than most people. The JWST mirror is about 2 stories tall. And JWST's orbit is much further away. Hubble orbits around the Earth. JWST goes past the moon to about, again, a little bit under 1 million miles, or 1.5 million kilometers, whatever your unit of choice happens to be. So unlike Hubble, which had multiple servicing missions, JWST has to get it right the first time. Another complication is that Hubble was able to launch as is, while JWST has to be folded up and then unfurled. So over the past 2 years or so, JWST was in Northrop Grumman in California, going through many series of extensive tests. And then in September 28th, late September, JWST was packed up very, very carefully, put on a boat, and sent by ship, avoiding the pirates, going through the Panama Canal, to land at its launch site in French Guiana. There, it's gone through another series of tests at the launch site, and is now being prepared to go into its launch configuration for a December 18th launch date. And that's where the fun begins. Sometimes after launch when a rocket reaches outer space, you can breathe a big sigh of relief. Not for us. This is where we start deploying the telescope and then start commissioning. 33 minutes after launch, the solar array deploys, and this is what powers the spacecraft. And then it's followed by the deployment of the high gain antenna about 2 hours after launch. And this is how JWST will communicate with the ground and send data, the wonderful data that it takes, down to Earth so we could archive it. 2.4 days after launch, JWST waves to the moon. 2.7 days after launch is the deployment of JWST pallets. These are the pallets that hold the sun shield. First, the forward pallet deploys, and then the pallet behind deploys. 3 days after launch, the tower assembly extends, and this is what moves the telescope and the detectors, which are right behind the telescope, from the spacecraft bus. And that's moved about 2 meters from each other. And this is, again, to minimize any heat from the spacecraft bus that would serve as a background to the telescope. 5.5 days after launch is deployment of the sun shield boom, first on one side, then on the other side. I kind of feel like, even though this is sped up, it feels like this video still goes too slowly when I show it in public talks. I don't have much to say to this video. And then there's the full sun shield deployment. The sun shield is unfolded. The tensions in the sun shield membranes increase. And then the 5 separate layers of the sun shield separate from each other. 6 days after launch, the secondary mirror deploys. And about 9 days after launch, the side wings of the primary mirror unfold and lock into place. At this point, the telescope continues to cool as it flies towards its orbit at L2, and it reaches L2 about a month after launch. But at that point, we're still not ready for the science program to begin. That's when we start commissioning, and that's where things start getting really busy for the JWST instrument teams, including folks like myself. 30 to 90 days after launch, we turn the instruments on, we do initial checkout, we focus the telescope. 90 to 120 days after launch, we do detector characterization, compare what we see in flight with data that we have from ground testing in the cryo chamber. And then the last 60 days, things get extremely busy when we have observations for every observing mode. We do a preliminary calibration so we could ask the question that many of us have been waiting for an affirmative answer to for a bunch of years. Are we ready for science? And then once commissioning ends, science begins. And there's going to be a lot that JWST is going to do within its first year of science programs. And you're going to be hearing about some of that in upcoming talks in this series. Christine Chen will tell you about planets around other stars. Elena Sabi will tell you about star formation. Nimish Hathi will tell you about galaxy evolution. I'll talk a little bit about what JWST will tell us about the early universe. And it'll tell us about the early universe by doing surveys which is when you take a telescope and you just stare at a patch of sky and see what you observe. And so many people might be aware of this from the 1995 Hubble Deep Field, which in many ways was kind of groundbreaking. This is where Hubble stared at a blank patch of sky that was smaller than the size of the moon, and it just stared at that part of sky for about 10 days. And what we saw were thousands of galaxies. Future surveys with the Hubble telescope have gone deeper and deeper, probing to further distances and probing further back in time. The deepest survey yet from the Hubble Ultra Deep Field goes back to a time when the universe was between 400 to 500 million years old. For reference, the universe is 13.7 billion years old. So this is 0.4 to 0.5 billion years after the Big Bang. And this is the limit that Hubble is really able to see. Any galaxies that are further away from that, any of those stars giving off ultraviolet light, as it travels through the universe, that light gets shifted to infrared wavelengths that are beyond where Hubble is able to view. So we really need JWST to probe deeper. So JWST will be able to probe to a time that is 200 million years after the Big Bang, and be able to observe the first galaxies, the first black holes, and the end of the cosmic dark ages. And it will be observing these legacy fields that Hubble and other great observatories like Chandra and Spitzer have observed before it. And I study black holes, so I'm very interested to see what we'll learn about the first generation of black holes. So what is it that we know now, and what are the mysteries that will be unlocked by JWST? Black holes are the natural end product of stellar evolution. Stars that are anywhere from 3 to 4 times more massive than our own sun end their lives in a violent supernova explosion that sends a shockwave careening into interstellar space, leaving behind the dense remnant, the core of that star. And if that core is dense enough, it collapses under its gravity to form a black hole. These types of objects are what we call stellar mass black holes because they're about 3 to maybe 20 times heavier than our own sun. Though with gravitational waves, we have discovered black holes that are a little bit heavier than this. That could be 20 to 100 times heavier than our sun. And it is a little bit of a challenge explaining how those got to be to those masses. There's another class of black holes, the ones that I study, that live in the centers of galaxies. We call these supermassive black holes because they are anywhere from millions to maybe even billions of times heavier than our own sun. And most of the time, these black holes are dormant. But sometimes we catch them in the act where they're growing by actively consuming nearby matter. Material that can't escape the clutches of the black hole will spiral into it. And in that process, when it's spiraling into the black hole, it gives off lots of light and it energizes its surroundings. And those processes form very unique signatures that we could observe to identify galaxies hosting these growing black holes. And we call these objects active galactic nuclei, or AGN. And because this process is so energetic and so powerful, we are able to observe AGN from the nearby universe to very, very far away. So one of the main questions in our field is, how did the first supermassive black holes form? How do you get from this little guy on the left that is maybe 20 times heavier than our own sun to something that is millions to billions of times heavier than our own sun? we could use some clues from what we've discovered so far to get some insight to answer this question. Within the first billion years of the universe, we've so far discovered 200 of these active galactic nuclei, these growing supermassive black holes. And when we've estimated their masses, many of them seem to be in this range where they're between 10 million to 10 billion suns. Well, that does not give them enough time to grow from these little guys on the left. For an object that is 20 times heavier than our own sun, there's just not enough time to just force feed it material for it to grow up to be that size. So a lot of work has gone into theoretically to propose what the seeds of the first supermassive black holes could be. We know that the first generation of stars, these so-called population 3 stars, are more massive than the stars around us today. And so when those stars age and go supernova, they'll leave behind a more massive black hole. And those remnants could be about 100 times that of our sun. Some stars live in clusters, which are gravitationally bound objects where the stars orbit around each other. And sometimes those stars will collide. So you start out with this first population of stars that are massive to begin with. If they're in a cluster and they collide and they form an even more massive star, and then that more massive star goes supernova, leaves a black hole, that black hole is going to be a heavier mass than what we saw in the last slide. So that mass range could be between 100 to 10,000 times that of our sun. It could be that in these stellar clusters, the stars maybe don't collide, or maybe some of them don't collide, but they go through their lives, they leave relic black holes. Those black holes then merge and form a bigger black hole that is, again, between masses of 100 to 10,000 suns. Or you could mostly pass a star phase altogether with what's called the direct collapse of a gas cloud. So these are primordial gas clouds that are about 100 billion times more massive than our sun. And they could contract to form a supermassive star that's very short-lived, that keeps on gathering more and more matter and collapses into a heavy black hole that could have masses between 10,000 to maybe even 1 million times that of our sun. So this would leave behind the heaviest seed of any scenario we've seen yet, but the conditions to support this are relatively rare, so it's a question of how common this could have been in the early universe. The most distant AGN to date that we've discovered lies at a distance that corresponds to 670 million years after the Big Bang. And this is a stunning, beautiful artist representation of what that might look like. The actual data are not as visually striking, but it does tell you a lot, and there is beauty in that data. So this is the actual image. And the 3 panels on the left are the panels in visible light, and the 2 panels on the right are the panels in infrared light. And the cyan circle shows you where the object is. In the left 3 panels, in visible light images, you see a whole lot of nothing, while in the infrared panels, you do see the object. So here we have an object that is bright in the infrared, but dim in the visible. So if we go back to the beginning of the talk, what could explain this? It could be something in our own solar system or in our own galaxy that is just cool and gives off more light infrared wavelengths. It could be something that's extragalactic, but that's very dusty. Or it could be an object so far away that the optical or ultraviolet light got redshifted into the infrared band pass. The way to answer this question is to get more data. As astronomers, you always want to get more data. But for this, you really do need to get more data to identify what the object is. And you do this by getting a spectrum which disperses the light so you could study its chemical composition. And that tells you what the object is, and it also tells you how far away the object is from us. And when this research team did that, the spectra unambiguously showed that this object is a growing supermassive black hole 670 million years after the Big Bang. What you're seeing in the infrared light images was originally ultraviolet light from that galaxy, or from the material right around the black hole. From the spectrum, they're also able to measure or estimate the mass of the black hole, and they found that the mass is about 1 billion times that of our sun. So this is the most distant AGN ever found, and it already has a black hole mass of 1 billion times that of our sun, but it only had 400 to 570 million years to grow to that size. I know 400 to 570 million years sounds like a lot, but it's not that much time if you want to build up 1 billion solar masses worth of bulk. So they proposed that this is probably something where the direct collapse seeding mechanism makes the most sense, because if you start out with a seed mass of 10,000 to 100,000 suns, then you could grow up enough mass to get to this size by this time in the universe. So what we've discovered in the early universe when it comes to these supermassive black holes is just the tip of the iceberg. JWST will reveal the whole iceberg. We'll be able to see the first generation of black holes, the ones even further away than we're able to now. And we'll get larger number of those that have been in existence within the first billion years of the universe. Then we can start asking what masses are typical. What we've been observing so far just might be outliers. And maybe the reason why all these black holes seem so massive is just because they've been easier for us to discover. We wouldn't want to say that we know everything about a population if we've only talked to a couple of people. We really need to observe the fuller population to have an idea of how these first generation of black holes came to be, and track what their seeding mechanisms are. I think there's probably multiple pathways, but we do have questions about which one is more common and what could we rule out for which objects. And from this, we can understand not only the black holes, but how they affect the galaxies in which they live, because there are many observations that indicate that there's some coevolution between these black holes and these galaxies. From this, we'll be able to track how galaxies and black holes have evolved from the infant universe to the present day. And that it could even shed light on how our own Milky Way galaxy came to be. So while I focused on the early universe, there are many discoveries closer to home that JWST will make, which you'll hear about in upcoming talks in these series. And JWST, being the most complex observatory ever built by humankind, I think is inspirational. It shows that if you really want to dream big, you have to undertake what's challenging. And though we have an idea of what the first year of science observations will be, because those programs are approved, and we have ideas of what questions those data will help us answer, there are bound to be discoveries that we can't even anticipate now. And the Hubble Deep Field is an iconic example of this. The Hubble director at the time put his reputation on the line for those observations, to stare at an empty piece of sky for 10 days. Now we can't even imagine sending telescopes into space without observing those areas of the sky. What is that discovery for JWST going to be? I don't know the answer to that, but that's part of what makes this so exciting. So there's going to be a lot that's happening this next year and a half. Join us on this journey as we learn about the universe both near and far. Thank you for your time.
Wow, thank you, Steph. This was amazing. I'm so excited. Every week I get more excited, and I also get so much more I get so much more nervous. I can't imagine how nervous y'all are, and because you're working on it.
Yeah.
You want to go ahead and stop share, and we'll come back together
Sure.
and do questions. If you have a question for Dr. LaMassa, you can raise your hand or you can put it into the chat box and we can do that. Happy to, you have the people on the front lines of science right here at your fingertips. Don't pass up this opportunity to ask her a question. I had a question about the cryo generator, the thing that keeps it extra cold up there. How is that powered?
Oh man. That is a great question. I actually don't know. Maybe from the solar arrays. So the solar arrays are powering the instruments. I believe it's powering the cryo cooler, but don't quote me on that.
I won't, and we'll try to figure that out for future. But anyway, that was just a question I had. We have Alan mentions in all of the photos and depictions of the mirror array, they're yellow. Why are they yellow?
Yeah. So the mirror segments are coated in gold. Is the short answer. They're beryllium with a gold coating because it's very reflective.
And Brian asks, why French Guiana?
Yeah, because it's near the equator, so it's just easier to send things up into space, into orbit from there.
Jack, what are gravitational waves? And will James detect them?
Okay, what are gravitational waves? So JWST is not going to detect gravitational waves. Gravitational waves are ripples in space-time that occur when you have two massive objects that orbit around each other and eventually collapse. So there was the first detection of gravitational waves in, oh geez, I forget the year, 2017, 2016 or 20, I think it was 2016, several years ago. Super exciting. And what's been detected so far for gravitational waves are from ground-based observatories, these interferometers that are sensitive to the merging of compact objects that are about maybe 10 times the mass of our sun to maybe 100 to 200 times the mass of our sun. So what's mostly been observed are the merging of black holes, sometimes merging of black holes and neutron stars. There was one case where there was a gamma ray burst associated with the merger of a neutron star with the black hole, and that was really cool. And it's just been kind of, whenever a gravitational wave event goes off, astronomers who study these things go to telescopes around the world to try to see if they could find what's called the electromagnetic signature, which is the light from that event. And especially with one of the first gravitational wave discoveries having the signature, this gamma ray burst that was observed by the Fermi Space Telescope, there were thoughts that like, oh, we should see this more often, and there haven't been any of those yet. So that's also kind of telling us a little bit about what could be causing them. There is a mission that will be launched in the 2030s, mostly led from ESA, which is a gravitational wave observatory in space that will be capable of observing the mergers, the signatures from gravitational waves from the mergers of supermassive black holes. And that will be really cool. So while JWST doesn't observe gravitational waves are part of what we call multi-messenger astronomy, because it's a way to get messages about what's going on in outer space that's not relying on light. And so there's this complementarity where you could use gravitational waves to learn about some types of objects and electromagnetic waves to also learn about that. And taken together, it really teaches us a lot about physics and the universe. So there might be cases where JWST might study, might follow up gravitational wave discoveries.
We have Dan also wants to know, and I concur. Do you have a plan for being able to sleep during those anxious first days of unfurling?
Oh geez, yeah, I don't know. Yeah, I honestly I'm just trying to get to like the launch date. If we just get there, I don't know. Like I'll worry about that. Yeah, it's going to be, yeah. Probably there'll be some sleepless nights.
Natalie is interested, do you think that James Webb will provide any insight into the moments just after the Big Bang, including inflation and the possibility of a resulting multiverse?
Okay, so that's a really cool question. Like the furthest that, so the short answer is no. So that might sound kind of sad, because the furthest that JWST can see will be 200 million years after the Big Bang. It's not going to really be able to see before then. And part of that is the wavelength that it's sensitive to. If you're really want to learn about inflation, that where you want to look is at the microwave wavelengths, the cosmic microwave background. And so there are even plans to augment our abilities to observe within that regime. And also for what JWST is more primed to look at are things kind of after that, after you've formed stars. So you have this time after the universe where you just have like hydrogen and helium, then it takes some time for things to, form atoms and collapse and form stars and heat up. And so, the stuff that's kind of more primordial requires other instruments and other telescopes.
There you go. We need to go to, you said that was for microwave we had to get to?
Yep.
Yeah. Go back to our first, our icebreaker question. All of those different wavelengths are important. We need to be able to look at all of the different wavelengths to have a better understanding, a more comprehensive understanding. Barbara, will you be able to transmit images of the unfurling? So does James Webb have a selfie stick?
Does James Webb have a selfie stick? I don't think it does. Yeah, so I don't know that we'll be able to get images of that. We'll just know from like telemetry and other diagnostics how it's working. So I don't know, maybe people on the ground want to try to use telescope. Yeah, even if you try to observe from the ground, you wouldn't be able to resolve that, unfortunately.
We have also, the Natural History Society has a love letters to James Webb project going on. It's a Padlet. I'm going to put the link right here, so you can copy that link and put it into your browser, and you can add your love letter. What do you want James Webb to see? Well wishes for a bon voyage, to the good travels, good unfurling. So you please go there, add your messages to James Webb, see what other people have been writing as well. Jack, I agree. It is a fabulous talk, and gives us a lot to think about. And amazing that what we are doing. We set a challenge, and you don't know how to get there, and you figure out a way. So it's quite amazing. And I don't want to be the Debbie Downer, but what if there is a problem up there? I mean, what if there's a problem? What's going to happen? I'm not trying to put negative vibes out into the universe, but it's a question.
Yeah, and I think that's a very fair question to ask, especially, most people know that when Hubble was first launched, it needed help. Um, so so it kind of depends on what the problem is. So some of the things that we've even been doing, there's been a whole round of rehearsals that have happened over the past year and a half or so at Space Telescope, where we do these tasks where we kind of like pretend we're in commissioning, and it's a way to practice the staffing and like the protocols. But there are also anomalies that are injected into these rehearsals to practice identifying what the anomaly is, figuring out a path to solve it, and a path to get back to science operations. So there has been some work to try to sketch out some things that, if this doesn't work well, what are we going to do? And it's also true that most space telescopes actually aren't serviceable, and those work. And sometimes things happen, especially as things get older. Some of the capabilities might be different than they were when it was first launched, but you work with what you have and you maximize the science return. I mean, as I mentioned, I was a mission planner for the Chandra X-ray Observatory, and there were times we would get kind of snarky and be like, well, we worked right the first time. We didn't need any servicing missions. So like NASA's done this. It's certainly, there's certainly legacy of things being successful. And it also, JWST has gone through just so much ground testing that there's a lot that has to go right, but all of that has been tested, and it's been tested very thoroughly.
Alan was interested, when did you first get interested in space?
Yeah, sometime when I was young. I don't know, I just always kind of thought outer space was cool, and then I never grew up. And so when I was just like, oh, astronomy, can people do that for a living? Okay, I'll do that. And it's kind of worked out somewhat. It's not always been easy. It's hard. It turns out it's hard, but it's been fun.
Let's see, Natalie asks, are there any other satellites or objects parked at L2? And could there be interference?
Yeah, so there are actually a couple of other observatories that are at L2. I'm trying to remember what they are. So I think Planck is one of them. So that's one that studies the microwave light. So it studies the cosmic microwave background. Herschel, which was a far infrared telescope, is also there. So there is a history of sending satellites and telescopes to L2. But in terms of collisions, I'm not really too worried about it. It's a pretty big space. So if you do the orbital mechanics right, then you're good.
Got it. All right. Any other questions for Steph while we have her here? Take advantage of this opportunity. I'm looking. Well, thank you everyone for coming. And I know that I feel a lot smarter than I did when we started today. So thank you, Dr. LaMassa, for making me and making everybody smarter and getting us even more excited about the James Webb Space Telescope launch and what it's going to teach us. I invite everybody to come back next week, next Thursday, for the part 3 of our James Webb Experience, and we will be learning about exoplanets, which is going to be quite exciting. And our Community Science Saturday, which is going to be in December, is actually a project called DIY Planet Search, where you can help identify, locate, and find exoplanets. So you definitely want to tune in for that as well. Again, your support is helpful in buying a raffle ticket. You want that fossilized dinosaur poop, because that's great, and everybody needs some fossilized dinosaur poop. So buy a raffle ticket, and we hope to see you very soon online or in person at one of our programs at the Natural History Society of Maryland. Everybody stay well and stay curious. And thank you again, Dr. LaMassa.
Well, thank you for having me, and thanks for showing up to learn about JWST.
Thank you, Steph.